Hello, welcome to another video in which I'm gonna try to solve some of your regular differential equation problems. So today we are gonna solve the problem of the isochronous curve. Let me write it. And then isochronous curve, it's a kind of curve that what happens is that you leave an object fall from different heights, and if the object is falling through this kind of curve, it happens that they will any object from different height will reach the lowest point of the curve at the same time. So let me show you this in a vertical circle. Like imagine that we have here a vertical circle and we have different objects. For example, we will have one here. We will have another one here, or starting from this other different height. And they all are gonna reach a point here that we're gonna call M. So what happens is that if it's an isochronous curve, it does not depend on time, and it does not really, they all reach the same point at the same time, and it does not really depend on the distance that they are going to have to cross to in order to get to the point M. So see this. This one would have to go this distance in order to reach the point. This other one will have to go the distance, and this third one will have to go through this distance. So the point here is to show that it's an isochronous curve. What does that mean? Well, that they all reach the point independently from the point M, independently of the distance. So basically, the time that they take, it does not depend on the path that they are taking. Okay, so let me call the radius of the circle R, and C is going to be the center. So this is C, and we will have several radius. So from here to here, we'll have a radius. This will be the radius as well. And of course, this is the radius too. So this is R, and this is R. So see here a little bit of geometry. This is a triangle that has two of the sides are the same, these two R's, and then it has another side that is different in length, which is this one. So this triangle is isosceles. Okay, let me call here this angle formed between this trajectory of this mass. There's three masses. This angle with the horizontal, we will call it theta. Okay, well, this is not too horizontal. Let's see. This is better. So I call this angle theta. So this angle is obviously 90 degrees minus theta. Okay. So applying a little bit of geometric properties, or just put in the theorem of cosine here, we can get what is this distance. Let me call it x. This is the distance from this mass to the point. So what is that x? Well, if we use the theorem of cosine, we'll have the r square is going to be all the two sides squares minus twice the two sides with the cosine of the angle between them, which is basically this one. Now we know 90 minus theta. Okay, but see that 90 minus theta, the cosine is exactly the sine of theta. So we can rewrite this very simply as the sine of theta. And from here, we can get how much is the distance. X squared is 2rx sine theta. So x is just 2r sine theta. So we need that. So now that we know that, what is the differential equation for a mass that is gonna drop? Well, this mass will have an acceleration, and this acceleration will be founded on its weight. So because it's a mass m. So this mass m will have a differential equation, which is exactly the mass times the acceleration will be the projection of the weight in the direction. So here would be the weight, and we would need the projection of the weight in this direction. So see here that this angle here, what is it? Well, that angle, if you take here and you take exactly this projection in this angle, sorry, this is really bad painted. Let me see. From here to here, you have its projection. This is exactly the cosine of 90 minus theta. So basically, it means that it's the sine of theta. Okay, so having that in mind, this is 90 minus theta. This is obvious because this is a rectangular triangle, and this is theta, so this will be theta minus 90 degrees minus theta. That means that the projection is exactly, yeah, as we said, the cosine, and then it goes by sine. So this would be the differential equation. Now, if we want to integrate it, well, the mass is going to disappear, and we're going to integrate the velocity in between. Velocity 0, we'll let it drop. So basically, it has no initial velocity, and we will integrate in between the time that this is gonna be descending. Okay, so realize that this is just g sine theta times t. And now, from here, if we want to integrate x, because we know that differential x with respect to t, it's exactly v. So if we integrate x, we will have to integrate this v. So x, it will be just the integral in between 0 and the initial point. But what's the initial point? Well, the initial point, we said that it was 2r sine theta. Okay, and that's the distance. That's precisely the x that we calculated. So that's the distance that is gonna I have to go through. It's going to be the integral of g sine theta t in between 2 times 0 on t. So from here, we get that 2r sine theta equals 1/2 of g sine theta t squared. And from here, we have, well, the signs are gonna disappear. And for here, we can get the t in terms of r and in terms of g. So r is exactly, well, t is exactly twice the square root of r divided by g. So what does this mean? Well, this actually means something important, which is that the time that it takes for a mass to fall from different heights, it's independent from the height that it's coming from. It only depends on g, the gravity, and it only depends on the radius of this circumference. So this is something interesting that as well is called isochronous, because the time, it's always the same, no matter from where I'm starting to fall on the descent. on how long is this path, the time to get to the lowest point here, M, and the circumference is going to be completely independent of that path. It would just only depend on the radius of the circumference.